As we start chapter 4, this is solving systems of linear equations. And I'll go through this here shortly. In fact, I'll go through some of it right now. This is a linear equation in two variables in standard form from chapter 3. This is another one. Now, because of the sub 1s, we're thinking that these equations are different, but they're both in standard form. Now, suppose we made a graph of this first equation, and it was this line right here. And we made a graph of the second equation, and it was this line right here. Well, what do you notice about this point right here? Well, they are intersecting. And what is the ordered pair of that point of intersection? Well, that point would be a solution for this equation and a solution for that equation. So in a sense, what would we be doing by graphing these? We would be solving this system of equations, we say simultaneously at the same time, because once we graph it and they intersect, that point of intersection is the answer for both of those equations up there. That unique ordered pair would be a solution for this one and a solution for that one. Now, to go on, and again, we'll repeat this in a little while, but suppose we graph this first equation and we got this line. And we graph the second equation and we got this line. Would they ever intersect? And you would say no, because the lines are parallel. They would not intersect. So there would be no solution for this. Now, if by chance, and as we looked at the equations, it didn't look like they were the same, but we did graph them. We graphed the first one, and then we graphed the second one, but the second one was right on top of the first one. It actually was the same as the first one, but sort of disguised in algebra, so to speak. Well, what would happen there? Well, a solution for one equation would be a solution for the other, since they're the same. And how many solutions would you have? Remember, this line extends to infinity in both directions. And we would say there would be an infinite number of solutions for something like this. So these are the three possibilities we're dealing with in chapter 4, systems of linear equations. We're looking for perhaps a unique point where they intersect, or if they don't intersect at all, there would be no solution for this one. And in this case, there would be an infinite number of solutions. Now, there are special ways to write these into the system, and we'll be going over that. But as we start section 1, solving systems of linear equations by graphing, we're going to do a little exercise first, which is this unique ordered pair a solution for this set of linear equations? And what do? Well, where the x is, we put the 12. Where the y is, we put the 6. And 2 times 12 is 24, minus 18 is 6. Yes, that would be a solution for this one. And if x is 12, then 2 times y, 2 times 6 is 12. Yes, this is a unique solution. That is a point where they would be intersecting. And here it diagrammatically shows you what's going on here. Now, later we will be graphing some information to try to pick out those points. How about an example 2? Is this a solution? Well, I've done the substitution. This is a 4. Minus 1 is 3. So it's good for this one. But then when I go 4 times a -1 is -4, and then minus a 2, which makes it a -2, this side is a -6, and that does not equal 6. So this is a no. And that's some of the stuff you'll be doing initially as you do the practice and the quiz me's. All right, so we're getting into now an example. They're giving us 2 equations. They're both in standard form. I want to give you a strategy for doing these. And my strategy would be, if they're both in standard form, then use that special T-chart. So if x is a 0, y is going to be, that's kind of tricky here because that's a fraction, 10/3, which is 3.3 or 3 1/3. That's not too good. But anyway, and then if y is a 0, then x is a -10. So in this case, a T-chart may not be the best. Well, let's do the other one. This one's easy. If x is 0, y is 2. And if y is 0, x is 2. So we have one good line here. So here they gave us one that was a little more challenging. So let's plot this first line. 0, 2, which would be right there, and 2, 0, which would be right there. And here's a case where your ruler comes in very handily, because you want to try to make a straight line here. Going off the ruler, you see what happens. All right. So, again, I don't have a 10 on my graph here, so I can't plot that one. So I'm going to solve it for y. So 3y equals a positive x, as I bring that x over, transpose it, plus 10. So I divide everything by 3. And I get y equals 1/3 x plus 3 1/3. So we got our y-intercept okay. So, but 3 1/3 is on the graph. So let's use that technique. We're going to plot 3 1/3, which is, this is 1, 2, 3 1/3 is right about there. And our slope is 3 for run. So I have to do this accurately. It's going to be right about there. And it's going to be up 1, right about there. Okay, now if you're using graph paper, if you're using your math lab, you know, this is a lot easier to do. So let's get our line here, and I'm shooting this. And to me, it looks like it's going to be a -1 and a 3. And I believe that is correct. So we did it. Now, keep in mind, if we were to plot this one, and we had graph paper, we could do that. That's probably out there somewhere. So that would be this point. And again, you have to be a little flexible. As we go on to this next one, example 4, we have our 2 equations. And again, this one doesn't lend itself to a T-chart very much because you get fractions. So I solved this first equation for y, and I got this. And then the second equation is just x equals 2, which is that vertical line. So I'm going to plot my y-intercept as a -2/3, which is right there. Then I'm going to do my run of -3 right there. my rise of 2 right there, and I get my 2 points. And as I carefully made my graph, this one came out again pretty well too. This is going to be a -2. Well, let's do the x first, 2, and then the y is a -2. All right, that's better. Okay. As we do example 5, notice our first 2 equations look different. But when I solve for y, put it in slope-intercept form, what do you notice? The slopes are the same. The y-intercepts are different. Here the y-intercept is 0, and these lines are parallel. So in a case like this, if you get parallel lines, you need to graph it, there is no solution. And they'll give you that as usually a series of choices. We've yet to do this one, but this example is coming up. Now in our last part of section 1 of chapter 4, we have 2 equations. Now as you look at these equations, equation 1 and equation 2, do they look the same? Well, no. But when you solve each equation for y, what do you note? They're the same equation. So when you plot one graph, x is a, y-intercept is a -3, and the slope is a 1/1, and that would actually bring it up to a 3 on the other line. There's a little technique there. And you plot your graph, and if I did the other one, it's right on top. What can you say about this? Well, it's this example here where they're actually the same line. So what would be the solution? Now, the way we write the solution for this is we put in what is called set builder notation. We use a brace, we say x comma y, that's our ordered pair, is such that, and you just write one of the equations. And in common sense, there's an infinite number of solutions. The lines are the same. Okay, well hopefully you're moving right along with your practice and quiz me's and ready to go on to our next topic. Now as you look at our next topic, you'll see that graphing has its difficulties sometimes, especially if you don't make the graph very well or it's not proper graph paper. So we're going to use algebraic methods for solving, and that's our next topic. All right, going on to example 8. I thought I was finished. But example 8, they want you to shoot these without graphing. What do you expect? Well, here's the first equation, here's the second. I solved each of them for y. What do you note? Well, our slopes are the same. The y-intercepts are different, so from chapter 3, for this one, without graphing, you know there's not going to be a solution. And for this one, 2 different graphs, I solved for y. Are they the same graph? No. Are they the same slope? No. And one's not perpendicular or anything, so these are going to intersect at one point. And if you did something like this, and you saw they were the same line without graphing, you knew it'd be an infinite number. Okay, this wraps it up. Well, I thought we were finished, but I see that we haven't gone over this vocabulary. And we have the word consistent systems is if they have at least one solution. So at least one solution, they are a consistent system. And then when you look at the lines, you see the equations are independent of each other. So consistent, has at least one solution, independent, different lines. Now, when the equations are parallel and there's no solution, we say it's an inconsistent system because there are no solutions and the lines are independent equations. And in the third case, we have consistent systems, but the equations are the same, so they are dependent equations. Remember, if you have at least one, this is the infinite one, so there's at least one, and then the equations are dependent because they're the same equation. Now that wraps it up.